Welcome to Brain Vision.
Okay, in this problem we have Compton scattering, where we have an incident X-ray that comes out of proton, initially at rest, and after the scattering, the X-ray deflects completely backwards at an angle of 180 degrees with its new wavelength, and the proton gets sent the other way with some momentum, energy, and velocity. Okay, so in this problem we're actually interested in finding a lambda such that the lambda actually changes by 10% as a result of the scattering. So this new lambda will be 1.1 times the original lambda. We also know that the angle of scattering is 180 degrees. That's really all we know. So in terms of equations to use, you really have to rely on the Compton scattering equation on its own. And that should be enough. Of course, that equation states that the X-ray after Compton scattering, its new wavelength is equal to its original wavelength plus h over mc times this quantity in parentheses that involves the scattering angle. So this is actually all we're going to need for this problem. We also, in terms of constants, need to know CH and the proton mass. C, of course, is 3 e to the 8 meters per second. We're going to go with a Planck constant of 6.626 e to the negative 34 joule seconds instead of electron volts. And of course, the proton mass is 2.76, or rather 1.67 e to the negative 27. So there's a lot of sevens there. It's easy to get tripped up. Kilograms. So this is all we're going to need. The crucial piece of information is being able to translate the problem, realizing that when it says the wavelength changes by 10%, what it really means is y prime is equal to 1.1 lambda, stating mathematically what the problem is trying to state. So we can quickly do this computation. It won't be that bad. Plug in what I just mentioned, that lambda prime is simply 1.1 lambda. We can set up the problem. And also noting that it's the cosine of 180 degrees because this X-ray is completely deflected backwards from which it came. We know the cosine of 180 degrees is negative 1. So everything's going to simplify. We'll first do that simplification before we do any additional ones. Because this is negative 1, in parentheses, we're going to have 1 minus 1, which is 2. So we're left with 2h over mc. We can combine these lambdas. They're the same lambda now. So 0.1 lambda equals 2h over mc. Isolating lambda. Dividing by 0.1 is the same thing as dividing by 1/10, which is the same thing as multiplying by 10. So we are left with this expression. I'm not going to box it. Let's get the number and then I'll box that answer. So putting in some real numbers, we have 6.626 e to the negative 34 joule seconds. Divide that all by the proton mass. It's really easy to substitute the electron mass on accident because most of these problems involve electrons. So we got to be extra careful here. Okay. And this number comes out to, taking a quick look at the calculator, comes out to 2.645 e negative 14 meters. So here's the result to box. So if you've done any of the other problems in this chapter, you'll notice that Most wavelengths are usually on the order of 10 to the negative 12 meters or picometers. This is significantly smaller than that. So this corresponds to a extremely large wavelength, or rather extremely small wavelength, thus extremely large energy. So this may not be one of the most practical results. It appears that to get complete reflection of 180 degrees and also get a 10% change in lambda of our light is a pretty considerable endeavor. Anyway, that's the calculation. That's it. Thank you very much.